welcome to Oddly Real. I'm Nem Stefanovic. Human beings have been aware of the effects of both electric and magnetic fields for thousands of years. For example, it was known that rubbing amber on fur or cloth could allow it to attract small pieces of feather or straw. This is due to static charge. Additionally, iron-rich ores called lodestones were occasionally discovered that possessed the ability to attract iron. Throughout history, these phenomena were treated as separate and independent. Only recently, in the past 200 years or so, has it been discovered that the electric and magnetic fields are actually two different manifestations of one single force, the electromagnetic force. Perhaps one of the most interesting and practical features of the electromagnetic force is the ability of a magnetic field to induce an electric field and a current in a process known as induction. We'll learn about how induction works, as well as the forces and transfer of energy associated with it. We'll also see some explicit examples of the application of induction. Induction is used in many modern-day electronic applications, such as inductive stoves, guitars, cell phone chargers, and electric generators. Consider the example of a conductive loop. On its own, it does not possess any electric current. However, if we move a bar magnet toward the loop, all of a sudden an electric current appears around the loop. If we stop moving the magnet, the current disappears. If we now pull the magnet away in the opposite direction, current reappears, but in the opposite direction. As long as there's a relative motion between the magnet and the loop, current will appear. Additionally, faster motion produces greater current. The process that creates this current is called induction, and we say that there is an induced current. Next, consider an example where there are two conductive loops facing each other with a little bit of separation. The first loop can be connected to a power source, like a battery, through a switch. If the switch is open, there is no electric current in either loop. If we close the switch, current will start to flow through the first loop, being supplied by energy from the battery. However, at the moment the switch is closed, we would see a flicker of electric current pass through the second loop and then vanish. Similarly, if we now open the switch, another flicker of current is detected in the second loop. These two examples illustrate the concept of induction. But what exactly is going on? A current in a loop is induced if there is a changing magnetic field passing through the loop. It's also not the amount of magnetic field passing through the loop that matters, but rather the rate of change of that magnetic field. We can define a quantity called magnetic flux, which is the amount of magnetic field passing through an area, like the interior of a loop. For example, the amount of magnetic flux passing perpendicularly through a loop is equal to the magnetic field strength, B, times the area of the loop, A. The size of the induced current is then proportional to the rate of change of the magnetic flux per unit of time. There are three main approaches to modifying the magnetic flux to produce an induced current. First, we can explicitly change the magnetic field strength passing through the loop. Second, we can change how much of the magnetic field passes through the loop. This can be done by physically changing the size of the loop or redirecting how much of the magnetic field goes through the loop. Third, we can change the angle by which the magnetic field passes through the loop. A narrower angle will make the area appear very small relative to the field lines passing through. If the magnetic field is in parallel to the face of the loop, that's equivalent to having no magnetic field entering the loop. There's an additional rule in induction that determines the direction of the current. This is called Lenz's law, and it states that the induced current is in the direction such that its magnetic field opposes the change in the magnetic field that produced it. For example, let's say the magnetic field is increasing from right to left across a conductive loop. That means the induced current will be in the direction such that its own magnetic field will oppose the field. That means it would want to generate a magnetic field in the opposite direction from left to right. In order to do that, the current would flow counterclockwise. Next, we look at the same loop, but now imagine the magnetic field is decreasing in strength, but still oriented from right to left. This will also generate a current, and that current will be in the direction needed to create a magnetic field to oppose the decreasing magnetic field. This means the induced magnetic field would point in the direction needed to try to strengthen the field. Thus, the magnetic field would need to point in the same direction, right to left. The induced current in the loop would have to be moving clockwise to produce this effect. One real-world application of induction can be found in electric guitars. Unlike acoustic guitars, which rely on a cavity within the guitar to naturally amplify sounds, electric guitars use pickups to convert sound frequencies into electrical currents. The pickups are magnets that are wrapped in a coil of wire. The magnet generates a local magnetization of the nearby guitar string. When the string is played, it vibrates, and its relative motion induces currents in the coil in the pickup. The frequency of the current matches the frequency of the vibrating string, which is ultimately transmitted to an amplifier and a speaker. Induction also involves forces and the transfer of energy. Lenz's law tells us that there's an opposition to the inducing magnetic field, which means there's also a force that opposes a magnet moving toward or away from a conducting loop. We have to do work or expend energy to apply this motion. The induced current in a conductor will encounter electrical resistance, which produces heat. The energy that we spend to move a magnet near a loop will ultimately get transferred into heat within the conductor. This can be measured as a small change in temperature. Additionally, some of the energy will also be radiated away in the form of electromagnetic radiation. Consider an example of a rectangular conductive loop in the presence of a magnetic field that is directed into the plane. If we hold one side of the loop and start pulling it out of the field, our action will decrease the amount of magnetic field passing through the loop. Moreover, this will result in an induced current through the loop. The moving charges within the current will feel a force due to the presence of a magnetic field. Those forces will be directed outward away from the body of the loop on the conductors within the magnetic field. Notice that two of the forces are pointing in opposite directions and are equal, thereby canceling out. However, there is one force present on the opposite end of the loop that will directly oppose our action to pull the loop out of the field. We have to do work to expend energy to counteract this force. This energy that we are adding to the system ends up being converted into heat within the loop. This can be verified as a small increase in the temperature of the conductor. Next, consider a situation where there's a solid metal body immersed in a magnetic field. If we pull on the body to bring it out of the magnetic field, the relative motion of the conductor to the magnetic field results in induced currents within the metal. However, the current is not restricted to flow in a simple circuit, like in the case of a conductive loop. Instead, the electrons within the body swirl around. We call these kinds of currents eddy currents. These eddy currents also encounter resistance to their motions within the conductive body, resulting in the generation of heat. A practical application of inductance can be found in inductive stoves. Here, the stovetop utilizes a conductive coil below its surface. An oscillating current is passed through the coil. This changing current produces a changing magnetic field. If there's conductive metal on the stovetop, like from a pan, those changing magnetic fields generate eddy currents within the pan, which also produces heat. The continuous application of this energy to the pan causes the pan to continue to heat up, even if the stovetop itself doesn't get hot. A similar principle is also used for wireless charging of electronic devices like cell phones. A coil in a charging pad can generate a variable magnetic field that can be picked up by a coil in the electronic device. The device then uses the induced current to charge a battery. Finally, perhaps the most interesting aspect of induction is the fact that we don't even need the presence of a conductive loop or solid body. In fact, a changing magnetic field produces an electric field all on its own in space. The phenomenon that we see as an induced current in a conductive loop is really this induced electric field pushing electrons within the material to flow. Moreover, this induced electric field is exactly like the electric field that surrounds a charged particle, but in this case, there is no charge or material present at all. There doesn't need to be a charge present to produce an electric field. For example, imagine a circular cross-section somewhere in space where there's a steadily increasing magnetic field. This results in induced electric fields in concentric circles throughout the region. So it's clear to see that if a conductive loop was present, the electric field would act around the loop to push electrons and induce a current. Yet, even without any material there, the electric field is produced. I hope you enjoyed this episode, and remember, oddly real, really interesting.